Utility companies across the United States employ varying methods for service changes. Pacific Gas and Electric (PG&E) in California utilizes temporary splices known as pigtails. These pigtails serve to connect the old and new service entrance conductors during the transition. The pigtails are constructed from a conductor material compatible with the existing service entrance conductors. Insulation is typically provided by heat shrink tubing, ensuring electrical safety and preventing accidental contact. The pigtails are attached to the old and new conductors using crimp connectors. These connectors create a secure and reliable electrical connection. Following the crimping process, electrical tape is applied over the connectors to provide an additional layer of insulation and protection against environmental factors. These temporary splices are generally removed within a few days once the new service is completely installed and operational. Southern California Edison, also in California, follows a similar approach, employing temporary splices referred to as pigtails for connecting the old and new service entrance conductors. The pigtails are typically made from number 10 American wire gauge (AUG) copper wire. Heat shrink tubing is used to insulate the pigtails, providing a protective barrier against electrical hazards. Crimp connectors are used to splice the pigtails to the old and new conductors, establishing an electrical connection. After crimping, electrical tape is applied to cover the connectors, enhancing insulation and protection. The temporary splices are typically removed within a few weeks, once the new service is fully installed and functioning correctly. National Grid, operating in Massachusetts, adopts a different approach, utilizing insulating displacement connectors (IDCs) to connect the new service entrance cable to the service drop during service changes. IDCs are specifically designed to pierce the insulation of the conductors and establish a direct electrical connection, eliminating the need for traditional splicing methods. After the IDC connection is made, electrical tape or heat shrink tubing is often applied to provide additional protection and insulation. These temporary connections are usually removed within a few weeks once the new service is fully installed and operational. Con Edison in New York City uses a method similar to Southern California Edison, employing number 10 American wire gauge copper pigtails to connect the old and new service entrance conductors. However, Con Edison differs in its splicing technique, opting for compression connectors instead of crimp connectors. Compression connectors create a tight and reliable electrical connection through mechanical compression. These temporary splices are typically removed within a few days once the new service is fully installed and operational. Beyond these specific utility practices, other common methods are employed across the United States. Some utilities utilize split bolts to connect the old and new service entrance conductors. Split bolts, typically made of aluminum or copper, are designed to securely hold two or more conductors together, creating an electrical connection. Other utilities employ mechanical lugs to connect the new service entrance cable to the service drop. Mechanical lugs resemble split bolts but incorporate a set screw that tightens down on the conductors, providing a secure mechanical and electrical connection. In situations where the service is buried underground, some utilities use underground splicing vaults to facilitate the connections between the old and new service entrance conductors. These vaults provide a protected environment for making and maintaining the connections. The specific practices employed by utility companies during service changes can vary significantly depending on factors such as local regulations, utility policies, and the specific characteristics of the electrical system. Electrical service changes involve working with energized conductors. It is essential to prioritize safety. Firstly, only qualified and trained personnel should perform electrical service changes. These individuals possess the knowledge, skills, and experience necessary to work safely with electricity. Secondly, always de-energize the circuit whenever possible. Before commencing any work on electrical conductors, the circuit should be de-energized to eliminate the risk of electric shock. Thirdly, use appropriate personal protective equipment, PPE. When working with energized conductors, it is essential to wear appropriate PPE, such as insulated gloves, safety glasses, and flame-resistant clothing. Fourthly, maintain safe distances. Maintain a safe distance from energized conductors to prevent accidental contact and arc flash hazards. Fifthly, inspect equipment before use. Before using any tools or equipment, inspect them carefully to ensure they are in good working condition and free from defects. Sixthly, follow lockout-tagout procedures. When de-energizing a circuit, follow proper lockout-tagout procedures to prevent accidental re-energization. Seventhly, use insulated tools. When working with energized conductors, use insulated tools specifically designed for electrical work. Eighthly, avoid working in wet conditions. Avoid working with electricity in wet conditions, as water can significantly increase the risk of electric shock. Ninthly, be aware of surroundings. Be aware of your surroundings and potential hazards, such as overhead power lines, confined spaces, and other workers. Tenthly, follow all applicable codes and standards. Adhere to all applicable electrical codes and standards, such as the National Electrical Code, NEC, to ensure safe and compliant installations. The NEC provides comprehensive guidelines for electrical installations covering aspects such as wiring methods, overcurrent protection, grounding, and equipment installation. Article 230.40 of the NEC addresses service entrance conductors, specifying requirements for their size, insulation, and protection. Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types, allowing for the selection of appropriate conductors for the intended application. Article 250 of the NEC covers grounding and bonding requirements, ensuring the safety of electrical systems by providing a low impedance path for fault currents. Section 110.16 of the NEC mandates arc flash hazard warnings, alerting personnel to the potential dangers of arc flash events. Article 408 of the NEC addresses switchboards and panel boards, specifying requirements for the construction, installation, and overcurrent protection. Understanding and adhering to these and other relevant sections of the NEC is crucial for ensuring the safety and reliability of electrical installations. Different types of electrical connectors are used in service changes, each with its own advantages and disadvantages. Crimp connectors provide a reliable and permanent connection when properly installed with the correct crimping tool. Compression connectors offer a similar level of reliability as crimp connectors but require a different type of installation tool. Insulating displacement connectors (ICs) offer a quick and easy way to connect conductors without the need for stripping or splicing. Split bolts provide a versatile connection method for joining multiple conductors, but they may require additional insulation to prevent accidental contact. Mechanical lugs offer a secure and adjustable connection for terminating conductors and equipment and enclosures. Underground splicing vaults provide a protected environment for making and maintaining underground electrical connections. Various types of conductors are used in electrical service changes, each with its own characteristics and applications. Copper conductors offer excellent conductivity and corrosion resistance, making them a popular choice for electrical wiring. Aluminum conductors are lighter and less expensive than copper but require larger sizes to achieve the same ampacity. Copper-clad aluminum conductors combine the benefits of both copper and aluminum, offering a lightweight and cost-effective alternative to solid copper conductors. Service entrance cable (SEC) is a type of cable specifically designed for service entrance applications, providing a durable and weather-resistant enclosure for the conductors. Underground feeder of cable is designed for underground installations, providing protection against moisture and physical damage. Electrical tape is used to insulate and protect electrical connections, providing a barrier against moisture, corrosion, and accidental contact. Heat shrink tubing provides a durable and waterproof insulation for electrical connections, conforming tightly to the shape of the connection when heated. Wire connectors, such as wire nuts and terminal blocks, provide a convenient and safe way to connect multiple conductors together. Conduit is used to protect electrical wiring from physical damage and environmental factors, providing a raceway for the conductors. Grounding electrodes, such as ground rods and grounding plates, are used to establish a connection to the earth, providing a path for fault currents to flow back to the source. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. Voltage testers are used to verify the presence or absence of voltage in electrical circuits, ensuring the safety of personnel working on electrical equipment. Ammeters are used to measure the current flowing in an electrical circuit, providing valuable information for troubleshooting and load balancing. Ohmmeters are used to measure the resistance of electrical circuits and components, helping to identify faults and verify the continuity of connections. Multimeters combine the functions of a voltmeter, ammeter, and ohmmeter into a single instrument, providing a versatile tool for electrical testing and troubleshooting. Infrared thermometers are used to measure the temperature of electrical equipment and connections, helping to identify hotspots and potential problems. Power quality analyzers are used to monitor and analyze the quality of electrical power, identifying issues such as voltage sags, swells, and harmonics. Cable testers are used to verify the integrity of electrical cables, ensuring that they are properly connected and free from faults. Insulation resistance testers, also known as megometers, are used to measure the insulation resistance of electrical wiring and equipment, identifying potential insulation breakdown and leakage currents. Ground resistance testers are used to measure the resistance of grounding systems, ensuring that they are providing an effective path for fault currents to flow back to the source. Arc flash personal protective equipment, PPE, includes items such as arc-rated clothing, face shields, and gloves, designed to protect personnel from the hazards of arc flash events. Lockout-tagout devices are used to prevent accidental re-energization of electrical circuits during maintenance and repair work. Ground fault circuit interrupters, GFCIs, are used to protect personnel from electric shock by detecting ground faults and interrupting the circuit. Surge protective devices, SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes and other events. Electrical enclosures are used to protect electrical equipment from environmental factors and unauthorized access. Wire markers are used to identify electrical wires and cables, making it easier to trace and troubleshoot circuits. Cable ties are used to bundle and secure electrical wires and cables, keeping them organized and preventing damage. Conduit fittings are used to connect conduit sections together into electrical enclosures, providing a secure and weatherproof connection. Grounding bushings are used to provide a low impedance path for ground currents to flow from metal conduit and enclosures to the grounding system. Bonding jumpers are used to connect metal parts of electrical equipment together, ensuring that they are all at the same potential. Antioxidant compounds are used to prevent corrosion on electrical connections, especially when dissimilar metals are used. Duct seal is used to seal conduit openings and prevent the entry of moisture and contaminants. Cable lubricant is used to reduce friction when pulling cables through conduit, making it easier to install long runs of wiring. Voltage-rated gloves are used to protect personnel from electric shock when working on energized electrical equipment. Safety glasses are used to protect the eyes from debris and other hazards. Flame-resistant clothing is used to protect personnel from burns in the event of an arc flash. Hard hats are used to protect the head from impacts and other hazards. Fall protection equipment is used to prevent falls when working at heights. First aid kits are used to provide immediate medical assistance in the event of an injury. Fire extinguishers are used to put out electrical fires. Proper planning and preparation are essential for a successful and safe electrical service change. Firstly, assess the existing electrical system to determine the scope of the work. Secondly, obtain all necessary permits and approvals from the local authorities. Thirdly, notify the utility company of the planned service change. Fourthly, schedule the work to minimize disruption to the customer. Fifthly, gather all necessary materials, tools, and equipment. Sixthly, conduct a safety briefing with all personnel involved in the work. Seventhly, establish a clear communication plan. Eighthly, inspect the work area for hazards. Ninthly, implement appropriate safety measures. Tenthly, document the work performed. The electrical system grounding refers to intentionally creating a low impedance path from electrical equipment to the earth. Firstly, it protects people from electrical shock hazards. Secondly, it stabilizes voltage during normal operation. Thirdly, it facilitates the operation of overcurrent protection devices. The NEC specifies detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for bonding metal parts of the system. The grounding electrode system typically consists of one or more ground rods, grounding plates, or underground metallic water pipes. The grounding electrode conductor connects the grounding electrode system to the electrical system's neutral point. Bonding jumpers are used to connect metal parts of the electrical system together, ensuring that they are all at the same potential. Ground fault circuit interrupters, GFCIs, are used to protect people from electric shock by detecting ground faults and interrupting the circuit. Surge protective devices, SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes and other events. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. Understanding the principles of electrical safety and following safe work practices are crucial for preventing accidents and injuries when working with electricity. Firstly, always assume that electrical circuits are energized. Secondly, never work on electrical equipment unless you are qualified and authorized to do so. Thirdly, use appropriate personal protective equipment, PPE. Fourthly, maintain safe distances from energized conductors. Fifthly, inspect tools and equipment before use. Sixthly, follow lockout-tagout procedures. Seventhly, use insulated tools. Eighthly, avoid working in wet conditions. Ninthly, be aware of your surroundings. Tenthly, follow all applicable codes and standards. Electrical distribution systems are designed to deliver electrical power from the utility company to individual customers. Firstly, overhead distribution systems use poles and wires to transmit electricity. Secondly, underground distribution systems use buried cables to transmit electricity. Thirdly, transformers are used to step down the voltage from the distribution level to the utilization level. Fourthly, switchgear is used to control and protect the electrical system. Fifthly, panel boards are used to distribute electricity to individual circuits within a building. Electrical metering is the process of measuring the amount of electricity consumed by a customer. Firstly, electromechanical meters use a rotating disc to measure electricity consumption. Secondly, electronic meters use digital technology to measure electricity consumption. Thirdly, smart meters provide advanced features such as remote meter reading and time of use pricing. The electrical service upgrades are often necessary to accommodate increased electrical loads. Firstly, assess the existing electrical system to determine its capacity. Secondly, determine the new electrical load requirements. Thirdly, select appropriate service entrance conductors, overcurrent protection devices, and panel boards. Fourthly, install the new electrical equipment in accordance with applicable codes and standards. Fifthly, test the new electrical system to ensure it is functioning properly. Electrical troubleshooting is the process of identifying and resolving electrical problems. Firstly, gather information about the problem. Secondly, inspect the electrical system for obvious signs of damage. Thirdly, use a multimeter to measure voltage, current, and resistance. Fourthly, use a circuit tracer to identify the path of electrical circuits. Fifthly, consult with a qualified electrician if you are unable to resolve the problem. The NEC is a comprehensive set of standards for electrical installations in the United States. Firstly, it is updated every 3 years. Secondly, it covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Thirdly, it is adopted by most states and local jurisdictions. Electrical safety training is essential for all workers who work with electricity. Firstly, it provides workers with the knowledge and skills necessary to work safely with electricity. Secondly, it helps workers to identify and avoid electrical hazards. Thirdly, it reduces the risk of electrical accidents and injuries. Electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. Staying up to date on the latest codes and standards is essential for ensuring the safety and compliance of electrical installations. Working with electricity can be dangerous, but by following safe work practices and adhering to applicable codes and standards, the risks can be minimized.